In this video, we're going to take a look at both independent and dependent random variables. So for independent random variables, we'll go ahead and start with just a definition for that. And so for our definition here, let y1 have a distribution function that is given by this. Y2 has a distribution function given by this. And if they have a joint distribution function shown here, then y1 and y2 are independent if and only if the joint distribution function, f of y1, y2, is equal to the product of each of those individual distribution functions. Right, and that needs to be true no matter what pair of y1 and y2 you might choose. If they're not, if the two random variables are not independent, then they are dependent. So one theorem that is worthwhile when you are working with these is if y1 and y2 are discrete random variables with a joint probability function, p of y1, y2, then the marginal and marginal probability functions, p1 of y1 and p2 of y2, then y1 and y2 are independent if and only if that joint probability function is equal to the product of the marginal probability functions for every pair of y1, y2 that we might have. And we have a similar thing for continuous random variables dealing with the joint density function and marginal density functions, respectively. So for those, when we have independence if and only if the joint density function between the two random variables is the product of the two marginal density functions. And notice that this is an if and only if, so it is sufficient to say we know that it's a product of each of the marginal density functions, so it has to be independent. Or you could say if it's independent, we know that it has to be, the joint density has to be the product of the marginal densities. All right, so let's take a look at one example in this video, and then we'll follow it up with some other examples in some following videos. So here we're going to take a look at a discrete example. Consider the experiment of tossing a pair of dice with random variables defined as follows. Right, so y1 is the number of dots appearing on die 1, and y2 is the number of dots appearing on die 2. So there, that joint probability density function, here we can have the value that shows up on y1 and y2. So those values could be 1, 2, 3, 4, 5, or 6. For y2, the values could also be 1, 2, 3, 4, 5, or 6. The probability that the first one is a 1 and the second one is also a 1 is 1 out of 36, 1 out of 36, 1 out of 36, 1 out of 36. And this will be true all the way throughout this table, right? Every single one of those values is going to be 1 out of 36. There are 36 possible rolls of the dice that we could get, and we've described each one of those possibilities. So this one that I'm getting ready to write right here is rolling a 3 with the first die and a 2 with the second die. The probability of that happening is 1 out of 36. All right, so everything in here, this is describing the joint probability function for our two random variables as defined up here. if we take the row sums, so this total right here, the row sums, those are for a particular choice of y1. It is adding up over every value of y2. So that row sum of 6 over 36, or 1/6, that is the marginal density or the marginal probability of getting y1 equal to 1. And we actually get 1/6 for each of these. So those were our marginal probabilities for y1. For y2, instead of taking row sums, we can take column sums. And we will notice that if we take column sums, those totals are also going to be 1/6. So each of those are 1/6, and so we notice that any one of these values in here, so let me choose a particular one, so like right there, that's the probability of getting a 2 first and then a 3. That is that 1/36 we could also find by taking this 1/6 times this 1/6. And that's true all the way throughout this table. We could take the product of the two marginal densities to get every single choice, every single joint. We can take the product of each of the marginal probabilities to get the joint probabilities. So it is independent. Right? The probability of y1, y2 does in fact equal the marginal probability of y1 times the marginal probability of y2 for all choices of y1 and y2. All right, we'll take another look at another example in the next video.